lecture is entitled Think Fast, and it's designed to introduce you to the next kinematics motion equation, the third one. It says fast is fine, but accuracy is everything, from Wyatt Earp. So the learning goals for this lecture are that students will be able to determine the situations in which final velocity cannot easily be measured. There's quite a few. And determine the origin of the third motion equation. You should be able to algebraically determine to obtain this equation. And then you should be able to determine any unknown for this particular equation. Now there are some extended questions in which you have to use something called the quadratic formula from math. Now that is a bonus type question, and you will see one. It is generally considered to be a bonus question, but make sure you talk to your teacher about their expectations for you for those particular problems. So the Think Fast investigation. So what we did is we dropped a meter stick and we wanted to see what our reaction time was. And we actually used this equation, a different form of this equation, but we still used this equation in order to determine what your reaction time was. So it didn't look quite like this because we dropped it. And when we dropped it, we kind of canceled through this term. And then we rearranged it to solve for time, but it's the same equation. So how did we arrive at this equation? And we did that this way. Now this looks like it's really complicated, but basically what I'm doing is I'm starting with the first two equations that we've learned. And what I'm doing is I'm rearranging those equations to solve for an unknown variable. I'm trying to solve for something that I'm trying to eliminate. So I take this first equation and I rearrange it to solve for final velocity. And so the first thing I do is I start to isolate it. I multiply both sides by delta t, and it crosses out on the right. Then I end up adding vi to both sides, and I get the equation vf equals vi plus at. A lot of times this is more common in textbooks than our a equals vf minus vi over t. So you see this equation quite a bit. So now you have a vf here and a vf here. You can take what vf here equals and you can substitute it in. And that's what you see in this next step. You see where they've substituted in, and now they start to simplify. So you have a vi here and a vi here, so that would add to 2vi, and then you have plus at. Now that's in the parentheses, and then you have the delta t on the outside, and you have the 1/2 here. Well, when you distribute the t to both of these, this actually becomes t squared, as you see, because t times at is at squared. And vi times t is vit. There should be a t here. And then the 1/2 gets distributed, it cancels the 2 out, and then the 1/2 doesn't get canceled out over here. So you get the equation, which is our next common equation, which is this delta d equals vit plus 1/2 at squared. And this is the third kinematics motion equation, and what it's used for is it's used to measure for situations in which final velocity is not easily measured. When you drop the meter stick, it was very difficult for you to measure the final velocity with a photo gate because the meter stick was so long that it would have never stopped and allowed the laser to reform. So because of that, that's not a situation in which we could measure velocity any very easily at all. So instead what we did is we used other variables that were available to us. Now if you look, there's no new variables here, so they went ahead and filled this in for you, but you should be able to fill this in on your own. Displacement, initial velocity, time, and acceleration. You should know what all those are by now, and you should be able to use them moving forward. Okay, so let's go ahead and do an example. The example says determine the initial velocity of a car that decelerates. Remember, decelerates is a key word. 2 meters per second for 10 seconds when moving in a positive direction for 500 meters. So we're trying to solve for the initial velocity. Now I will tell you that this is a very, very difficult question. So before we do that, let's get started and say, okay, what do we know? We know that the acceleration is going to be a negative 2 meters per second squared. Okay. In addition to that, we know that the time is going to be 10 seconds. And then we know that it is moving in the positive direction for 500 meters. Delta D is 500 meters. And we're trying to solve for the initial velocity. So the equation that we have is delta D equals VIT plus 1 half at squared. Or when we plug in, we get 500 equals VIT plus 1 half negative 2 10 squared. Oh, this one wasn't as hard as I thought. This one is the easier one for us to take a look at. So we'll look at one that's a little bit more difficult later. So whenever you do this, you get 10 squared times 1 half times negative 2. These terms are going to cancel each other out with the exception of the negative. So you end up with 500 equals 10 VI. Forgot to substitute the 10 in there. 10 VI minus 100. Whenever you do this, this becomes 600 equals 10 VI. Whenever we add 100 to both sides, divide both sides by 10. And when we do that, we get VI equals 60 meters per second. So the initial velocity of the car was very fast. It was 60 meters per second. And even though it decelerated for a while, it still took quite a lot out of, it still traveled very, very far during that time frame. So we have example A2. It says determine the acceleration of a missile that starts from rest and accelerates for 2 seconds over 84 meters. So once again, we're trying to solve for something in which we do not have the final velocity. You have delta D is 84. You have the time is 2 seconds. And in this case, we're given the initial velocity is 0 because of the idea of it starting at rest. So if we move forward from there, we can say, all right, well, let's use our equation. Our equation is delta D equals VIT plus 1 half AT squared. Now, a lot of times when you use this equation, you'll have an initial velocity of 0. And the nice thing about having an initial velocity of 0 whenever you look at this particular equation is the fact that this entire term will cancel out. That makes this much more simpler to use. So whenever we do that, we can plug in our stuff. We can say 84 equals, we're going to do away with this whole term because 0 times t is still 0. 1 half a, and then we're trying to solve for a, and we have t squared. So 2 squared is 4, and 1 half times 4 is going to be 2, so now we have 84 equals 2a. You divide both sides by 2, and when you do that, you get 42 meters per second squared equals a. You should be able to do example A3, and you should be able to do it entirely on your own, and you should be able to get the answer delta D equals 75 meters. You should be able to work through the equation, pick out the given, and plug it in, and you should be able to do that on any sort of quiz that your teacher will have for you in class. Now, so far we've discussed nothing but horizontal problems. We've talked about cars on a road, people running, those sorts of things. But that doesn't tell most of the story. A lot of times you have situations in which things move vertically, like whenever you drop a ball. Whenever you drop a ball, whenever you're moving vertically, you tend to have extra information that you didn't have in other sort of problems. So the first thing that you have right away is if you drop a ball, as soon as you let go of the ball for the briefest instant, its velocity is 0. So whenever you see an object is dropped, you can automatically say, okay, well, the initial velocity is 0. And the second thing that you can tell is that the acceleration is going to be negative 9.8 meters per second squared. That is referred to as the acceleration due to gravity. And that does not change. Okay? If a ball is released, thrown up, let go, dropped, thrown down, the acceleration due to gravity takes over. Gravity does not change because you throw a ball upwards. Gravity does not change because the ball reaches the top of its path. Gravity does not change. So as long as we are on Earth and it is a vertical problem and it's not like a rocket or something like that, then the answer there is going to be negative 9.8 meters per second for the acceleration. So you need to make sure that you're aware of that because a lot of times people get those confused. Other than dropping something, you can throw an object down. Whenever you throw an object down, the initial velocity is down, therefore it is going to be negative. The acceleration is still going to be negative 9.8 meters per second squared. People say, oh, well, it must be positive because I'm throwing it down now instead of dropping it. No, gravity doesn't decide to change direction based on what you do. Gravity is always going to be negative 9.8 meters per second squared. Another thing that you can say is that the final velocity is going to be negative as well. And that kind of matches up with what we know. So negative 9.8 meters per second squared is always the acceleration, and the final velocity is going to be down. Also, one other common situation is what you get whenever you have an object that is at its highest point. At the highest point, an object goes up, 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 up. It reaches that highest point, and when it reaches that highest point, for the briefest of instants, it stops, and then it starts to come back down. Okay, it's the briefest of instants, but what you can say is at that very highest point, you have a velocity of 0. Now notice I don't say initial velocity is 0, I don't say final velocity is 0, because it depends on how you want to look at the problem. If you want to look at the problem for the first half, from up to the highest point, then you could say the final velocity is 0. But if you want to look at the problem from the top on the way down, you could say the initial velocity is 0. So this is one of the ways that you can kind of take a look at these, and you can see that there are several different ways to look at problems, and you need to be able to kind of manipulate this information in a way that best suits you. This is example B1, and this is a difficult question, so just be aware of that going in. We are going to have to use something called the quadratic formula, and this is considered to be an extension beyond a regular physics class. It says a ball is thrown upwards at 100 meters per second. How long will it take for the ball to be 10 meters from its starting position? So you should be aware of the fact that whenever you throw the ball up, it's going to go up and it's going to come back down. So because of that, there's actually going to be two places where it's at 10 meters, on the way up and on the way down. So you're probably not used to calculating problems in which you have two possible solutions, but the quadratic formula will help us determine that. So let's go ahead and take a look at what we have to begin with. The first thing we have is we have the initial velocity is 0. We have the displacement is 10 meters, and we also have the acceleration due to gravity is negative 9.8 meters per second squared. The equation that we're going to use is the same one. It's delta D equals VIT plus 1/2 AT squared. And people may be saying, well, how can this be different than the other ones? And you'll see whenever we plug in the numbers. Oh, excuse me, the initial velocity was 100. So now we say delta D is equal to, we've already got that there. We can say that 10 is equal to 100 T plus 1/2 A T squared. So whenever we do this, you can see that there's going to be a problem. We have 10 equals 100T minus 4.9T squared. Now what a lot of people try and do, and you cannot do this, is they like to say, oh, okay, well, I'll just combine these T terms and then divide. But this is a T and this is a T squared. You can't add those terms together. So instead what I'm going to do is I'm going to move them all to one side. I'm going to take this and I'm going to move it over to the other side. I'm going to take this, I'm going to move it to the other side. So I'm going to have 4.9 T squared minus 100T plus 10 equals 0. So whenever I do that, you now start to look at this and you say, okay, well, what do I do now? You should be familiar with the quadratic formula from math, where you can say that this is the A term, this is the B term, and this is the C term. The quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. That's a standard formula that you learned in Algebra 1. You've probably used it a lot more in Algebra 2, but this is what you use in order to solve two answer equations. So if we start to take a look at this, let's plug in our numbers. We say negative b. Well, b is already negative. So negative of negative 100 is a positive 100. Plus or minus the square root of b minus 4ac. And our c term was 10. So when we do 4 times 4.9 times 10, we get 196. So now we have 10,000 minus 196 is what is going to be in our square root value. So we basically have the value of 10,000, but let's go ahead and get our exact numbers. 9,804, and then all of that is divided by the term 2a, which was 9.8. So now what do we do? Do we take the positive? Do we take the minus? It tends that we're going to take both. We're going to take both answers. The red one will do positive first. So the first thing we need to do is find the square root of 9,804, and that ends up being 99. It's like 99.05, but we'll just go ahead and call it 99. So we'll cross that out and say 99. So 100 plus 99 is easy. It's 199. So 199 divided by 9.8 and gives us a first value, a time value of 20.3. But then we also have to take the minus value. So now we do 100 minus 99, which is 1, and we take that and divide by 9.8, and we get a value of 0.102 seconds. And does that make sense? We have one time that happens almost immediately. When you fire it up, it reaches 10 meters almost immediately. Then it goes all the way up, comes up, and comes all the way back down, and just before it strikes the ground, it passes 10 meters again. Like I said, this is a very difficult question in the sense that there's a lot going on. So go ahead and make sure you check with your teacher as far as what their expectations are for this level of problem. Example B2 says determine the displacement of a ball dropped 3 minutes after it was dropped. So the key thing here is it was dropped, so we can say the initial velocity is 0, the acceleration is negative 9.8 meters per second squared, and we can say that the time that it took was 180 seconds because we don't deal with minutes. And we are trying to solve for the displacement, delta D. So we can say delta D equals VIT plus 1/2 AT squared. Now, like we said, most of your problems are going to be either horizontal or it's going to be this situation where this VIT term cancels out. So we get delta D is going to equal 1/2 negative 9.8 times 180 squared. Now 180 squared is going to be a rather large number, so we do 180 times 180 times negative 9.8 divided by 2, or times 0.5. And when you do this, you actually get a number of negative 158,760. And people usually have a hard time with this negative number again. Remember, the negative just indicates direction, and in this case the direction is down. This is example B3. You should be able to determine all on your own that the answer is 45.2 seconds, and you should be able to reproduce that on any sort of quiz that your teacher will provide you.